So hi everyone, I'm Deanne Hargrave. We'll be looking at the role of geoscience in development process for offshore wind farms. Um, if you could go to the next slide, please. And thanks, Lane, for doing that for me. I have a few too many things going on here, and it really helps me if you do that, so I appreciate it. So I'm currently the geoscience manager for Atlantic Shores Offshore Wind. It's a joint venture between EDF Renewables and Shell New Energies. Atlantic Shores is made up of people from the two parent companies. As such, my direct employer is Shell, where I sit in the offshore wind technical team. I've been completing geoscience projects for shallow water development for over 20 years and specialize in geotechnical and geophysical survey planning and execution. I'm a strong advocate for new technology and always look for better ways to complete the task at hand. This is a large part of what I do as co-chair of the technology working group. That's a part of the Hydrographic Services Review Panel, which is a federal advisory committee. We focus on advising the NOAA administrator on various issues, including hydrographic survey priorities, technologies relating to operations, and ocean research. And that is me in the picture. That's I had hair before the chemo borrowed it for a little while, but I'm doing great, so no worries there, but it really is me. The focus of today's presentation is to take a high-level look at the role of geoscience in the development of offshore wind projects. In order to do that, we will be asking and discussing this list of questions, starting with what are the tools used to conduct these surveys? I'll touch on this briefly, while I think Kevin and Drew will probably expand on it in more detail. What kind of data are created? What is geophysical and geotechnical data, and how are they different? What is the purpose of conducting these surveys? How is the data used to inform regulatory and design considerations? When in the development process do these surveys occur? What data is collected? When and how does it impact the project? And will data collected from these surveys be made publicly available? And if so, when? Next slide, please. Perfect. I don't even have to tell you, Lane. Thank you. So data gathered during G&G surveys can be categorized into geophysical and geotechnical. Geophysical data is gathered with hole-mounted or towed sensors that emit sound in the water that reflects from the seafloor or subsurface. These sensors allow us to map large areas without touching the seafloor, but are limited to interpretation of the data. Geotechnical data is gathered to ground truth the geophysical interpretations. Geotechnical data includes physical samples of the seafloor and subsurface using various coring techniques. Vessels used to carry out this work are typically purpose-built. They're designed to stay offshore with a large technical crew for 3 to 4 weeks at a time, completing 24-hour operations. In order to protect species that are sensitive to the acoustic emissions of these operations, protected species observers are on board the vessels. Their job is to watch for protected species and assist the survey vessels with avoiding these animals. Sometimes this means shutting down operations until the protected species are far enough away not to be impacted. The onboard technical team includes 20 to 30 personnel, depending on the specific operation. Geotechnical drill ships require more personnel than geophysical surveys, and the teams are typically made up of a host of characters, including geologists, geotechnical engineers, geophysicists, seismic processors, equipment technicians, protected species observers, archaeologists, medics, HSE coordinators, data quality assurance representatives, and offshore project managers. Considerable shoreside support follows each vessel to help the operation run smoothly, including project managers, operations, logistics, and quality assurance. Although much of the G&G work requires these specialty vessels and crews, there are opportunities for developers to work with local fishing vessels and shoreside support facilities. Many of the smaller survey vessels working over the past few years have had shoreside operational support from local fishing docks, laydown yards, and storage facilities. And many developers are working with local fishing liaisons who use their vessels to scout for fishing gear in areas that are to be surveyed and help work through cooperative solutions. The next set of slides I'll show will include examples of the kinds of data that are acquired. And this is not a complete list. And Kevin and Carrie, I'm sure, will expand on this further in their presentations. So one example of data is bathymetry. I'm sure you're very familiar with it. Bathymetry is a three-dimensional mapping of the seafloor for water depths. The technology used is similar to a typical echo sounder or fish finder on a fishing vessel, but with a few key differences. The number of acoustic soundings that are collected simultaneously. For fish finders, they generate 1 ping per second, while a survey-grade multi-beam system generates over 100 pings in order to produce a swath of depth soundings that are accurate to within centimeters. The resulting resolution of the data is much higher. This image shows NOAA bathymetry in the background blue with resulting contours, while the survey-grade bathymetry in rainbow colors shows the dramatically higher resolution data that is gathered. This resolution is necessary for engineering and design, and it's also required by BOEM. Bathymetry data allows for detailed modeling and analysis of the seafloor geometry, which helps with planning for cable and foundation installation. The detailed data helps developers understand potential challenges for construction, including things like steep slopes that can make cable burial difficult. All attempts are made to avoid these challenging areas when selecting cable routes and foundation placements. Next slide, thank you. Another kind of data is side-scan sonar. Side-scan sonar images are two-dimensional representations of the seafloor. The data is used to map the extensive seafloor conditions, including areas of mobility, debris, and shipwrecks. Grab samples are used to ground truth the seabed soil material. Anthropogenic debris in side-scan sonar is investigated for coincidence with magnetic anomalies to help identify the debris type. Developers use this information to avoid installing cables or foundations where historically sensitive features have been located, and for avoiding other infrastructure such as buried communication cables. These locations are communicated to BOEM when they are found following the regulatory reporting protocol. Next slide, please. So in addition to mapping the seafloor surface, subsurface data are also acquired. High resolution, shallow seismic data is collected with two sources to meet the regulatory and design requirements for archaeological and geohazard characterization. The image shown here is the higher frequency sub-bottom profiler, which typically maps the subsurface to depths of 10 meters below the seafloor. This data is instrumental for planning the route and depth of burial of inter-array and export cables. A lower frequency system is also used to map the subsurface to 100 meters below the mudline. This typically is only in the lease area, and the data is used for foundation design and location planning for the offshore wind turbines and substations. The next slide shows geotechnical cores that are collected with a few methods, but often result in recovery of soil that can be tested for strength indices in the laboratory. Alternately,
yeah, so Brittany got her key grinder in, so I'm calling her.
Excellent. Alternately, in addition to getting physical samples, in situ, in-place tests can be completed with shallow seabed cone penetrometer tests or deeper downhole CPTs. CPTs are tools that are pushed into the soil. The tools have sensors on them that measure how much force is required to advance through the soil. This directly translates to how strong are the soils. These in situ tests provide continuous profiles of soil strength, whereas laboratory tests only occur at discrete locations within the core. Geotechnical data is critical to not only provide engineering properties to the design team, but it is the key to ground truthing geophysical data. This leads to the next slide where we discuss the ground model. Data are gathered and brought together into the ground model, which is used to inform layout designs, foundation types, and burial depths. The data are gathered in the lease area and along export cable routes and used for geohazard, archaeological, and benthic clearance. The image here shows all of the sources of data that are input into the ground model. Experience data includes knowledge from local fishermen, including knowledge of shipwrecks that may not be accurately mapped on the NOAA charts. And I think Kevin will provide a deep dive into the ground model in his presentation. So when in the development process do these surveys occur? Geophysical and geotechnical surveys are an integral part of a project from first conception through to decommissioning. However, the greatest efforts occur during the development stage, also coinciding with the assess, select, and define stages of a project. Typically, this is completed in a phased approach that includes collecting preliminary or reconnaissance level geophysical data of the full lease area during the first season. This first investigation provides a basic understanding of site characteristics and variability. This data is the basis of the ground model, which helps inform the preliminary layout, including which portion of the lease to develop first if taking a phased approach. The ground model is used to select and clear the first round of geotechnical investigations. These investigations typically include 15 to 20 deep boreholes with downhole CPTs that provide reconnaissance level understanding of soil conditions and are used to ground truth the geophysical data. This information is fed into the ground model, resulting in a tool that can be used to select foundation types for turbines and substations. Do we want to do questions now or wait until the end? I saw a question pop up on the chat.
And I think it's okay to take them as you're most comfortable with.
Okay. What is the diameter and length of the core samples? Core samples, they're typically 3 to 4 inches in diameter. And if you're using a vibrocore, they would be 3 to 6 meters long. And if you're doing a borehole with a drill ship, they can be, the samples themselves are 1 meter long, but they can be taken at any depth down to 100 meters.
Okay. And there was another question in there. Do you record what animal life might be found in the core samples?
Yes, thank you. Yes, indeed. So benthic analyses are done on the cores. I think probably Drew can speak to that in a little bit more detail. So maybe we hold that question until Drew's presentation, if that's okay.
Sure thing. Thanks.
Okay. So we were talking about the next phase of the ground model. And so next you do a geophysical survey that provides full coverage of the area of potential effect at the regulatory required resolution for geohazard and archaeological clearance. And each time a new data set is collected, it is incorporated into the ground model to improve the robustness and usability for design and engineering. Finally, with version 3 of the ground model, the foundation locations are selected and discrete geotechnical investigations are completed at each location. This process can take as few as 2 years if you're very fortunate, but more generally requires 3 to 4 years of sequential work to fully complete. Next slide, please. So the data is used for various purposes throughout the entire project lifecycle, from planning and development through to decommissioning. The largest volume of data, as we just discussed, is collected during the planning and development stage to support planning, design, and installation of offshore wind turbines, substations, cables, etc. This has already been described in the previous slide, but in addition to this early data, it is also necessary to survey the precise location of cables and foundations to develop as-built or as-laid data sets. These are critical for managing the integrity of the infrastructure and will be used for the baseline to measure change over time. For example, the depth of burial of the cable and potential scour will be measured with geophysical tools throughout the life of the project. And finally, during decommissioning, geophysical surveys will cover the area of operations to confirm that decommissioning is complete and that lease conditions are met depending on the stipulations of the permit. And we'll conclude with, will the data that we've been talking about that's been collected from these surveys be made publicly available? And if so, when? I see another question. Can you discuss the burial depth of the cables? So I can't speak for all the developers here. I think each project is unique in the depth of burial, and there are a number of factors that play into that, including the characteristics of the site, the other users of the area, and so I think though in general I would say that depth of burial ranges between 1 to 3 meters depending on where you are.
And does the composition of the bottom come into play to determine how deep it's buried?
Yes, absolutely. So there are some sub-bottom or seafloor conditions where the seafloor is too hard to be able to bury the cable. In those cases, it's typically laid on top of the seafloor, and then protection is placed over the top of it.
Is this an appropriate time to discuss the protection that's placed, or not necessarily?
You know, I'm really not. That's outside of my G&G realm. I don't have too much to offer on that one.
I've got another one for you. Suppose you're in high energy sand and burying a cable that's 2 meters deep that can be uncovered easily by a storm. How would you address that? Yeah,
so typically where you have areas of mobile sediment like that, sand waves that move with storm events. Typically, cables are buried 2 meters below the surface where that mobility stops. So the sand waves are moving in a layer, and down below that is a layer that's fairly stable, and the cables are installed 2 meters below that stable layer.
Thank you.
And
Yeah, Deanne, if I could just add, you did a great job describing that. And one of the things that we look at when we look at recommending the burial depths of the cables are what are the different things that could impact the cable. Are there types of vessels that have certain size anchors in an area, and if they drop their anchor, how deep might the anchor penetrate below the seabed? And so that's one of the areas that we on the engineering side will look at the strength of those soils, what the seabed composition is, and then we'll look at the size of the anchors that could be dropped, and if the wind or environmental conditions are pulling the vessel and the anchor drags in the seafloor, how deep might it embed, and then we would provide recommendations of how deep that cable should be buried to reduce a hazard related to an anchor penetration. They also look at other activities that are occurring in the area, such as the types of fishing activities that could impact or interact with the seabed, and then provide recommendations of how deep the cable should be buried below to mitigate those potential hazards. And then, and again, Deanne accurately described trying to, in areas of mobile sediments, and I appreciate your perspective, Guy, on these storms really can move the sediments around quite a bit and change the bottom conditions. So that's another component that is typically integrated in the cable burial recommendation study is, are there areas of mobile sediments? How big are the sand waves? And how fast are they moving? Will they potentially expose the seabed or the cable on the seabed? And then if so, how do we get the cables to bury deeper? So one of the things that are done in sand wave areas is what they call pre-dredging or sweeping, dredging the sand wave to allow the cable installation tool to get it, 2 meters below that base of the mobile sediments. And then I think I would probably not have a whole lot more to offer on the cable burial protection, but the standard protection is, rock dump or concrete mats and concrete blankets, laid on the seafloor, and areas where you can't get the cable buried to depth that might be what's implemented, or when they cross over other cables, then they would use concrete mats to separate those cables.
Thanks, Kevin. So I suspect that we may want to do a totally separate educational webinar on cables, because I think we could probably go on for a really long time, and I know there's a ton of questions. And I do want to make sure that we get to Kevin and Drew's presentations. So maybe what we can do for now is, if you hold questions, you can either put them into the chat, or after each presentation, we could do some quick Q&A, and then at the end do a bigger Q&A if that works. I just want to make sure that we have enough time. So thanks.
Okay, noted, Annie. Thanks.
Sounds great. Well, I'm on my last slide, so we'll wrap this up here and pass on to Kevin and Drew. So the last thing I wanted to touch on is the construction operation plan, and I'm sure you're familiar with it. The COP. It's like the project's blueprint. It details what will be built, how it will be installed, where it will be located, and how it will be operated and maintained. Site characterization is a large part of the COP, and as we have demonstrated, can take several years to complete. These G&G campaigns are expensive, as some of the vessels can cost $50,000 to $100,000 per day, depending on the unit. A challenge for developers is phasing this data gathering in line with the project plan and timeline, such that the required information is available when needed to make project decisions, and conversely, that project decisions are made to inform the investigations. A risk to developers is that the project develops slightly out of sequence, which can lead to having to resurvey areas if there are design changes. Data collected during these various geophysical and geotechnical campaigns results in multiple terabytes of information. It exists in formats that require specialty software to review, and the data itself is not really that useful. It's the interpretation of the data, the work that Kevin and Drew do, and generation of the maps, charts, reports, statistics, and models that allow us to consume the information and understand what the data are showing. The resulting interpretation reports are included in COP submittals, and data are also delivered in coordination with the COP submittal. The volume of data is so large that it typically requires multiple hard drives. And after BOEM has received and reviewed the data, it is made available to the public as part of the COP. However, some information is sensitive and is kept confidential. For example, archaeological reports that have details of historically sensitive resources. But developers are always looking for ways to share data for common benefit. For example, MetOcean and LiDAR data is available through Maricruz from the Atlantic Shores buoy, and developers are actively looking for other opportunities to share information. I think that concludes it for me. I appreciate your interest in this topic. It's complex, multifaceted, and we're always improving through sharing this kind of information through forums like this. So I appreciate your attention. Thank you.
Thanks, Dan. And you can stay with us till 5, right?
Yeah, not a problem.
Perfect. So in that case, I would ask if there's any sort of, clarifying questions now, and if not, if there's deeper questions, we can hold them till the end of the third presentation. Just make sure there's no hands raised. I don't see any. Okay, great.
I have a question in the chat room.
Yeah, okay, sorry, Pete, I didn't see that. Okay, so there's a question in the chat. Are cable depth the same within a grid versus transmission from the grid to shore?
Again, that's a project by project answer to that. I could really only speak to Atlantic Shores, and for Atlantic Shores, yes, it's the same.
Great, and Peter, we'll keep a list of these for a follow-up webinar on cables. I think this sounds like there's a lot of interest. And one more in the chat. After a protected resource sighting, how far do you have to be to resume testing?
Yeah, that's a great question. It depends on it depends on the protected species. They have, because they have different exclusion zones, or distances in which they could be affected by the sound source that's coming from the operation. Likewise, the different pieces of equipment on the vessel have different radii of impact. But typically it's between 50 and 200 meters, depending on what the species is.
Thanks. Okay, let's move on. Is Kevin next or is it Drew?
Kevin.
Kevin.
Kevin, okay, perfect.
All right. So do I need to request control? Is that how that works?
You should just be able to go to the bottom of your screen and select the screen share upward facing arrow.
Kevin, just move your mouse to the bottom. There's a little bright green arrow down there.
I'm just trying to make sure I'm gonna select the right
There you go.
two and
Success.
all right. All right. Okay, so we should be seeing the title slide. And all right. Okay, so good afternoon, everybody. My name is Kevin Smith. I'm a senior consultant at Fugro with an area of expertise in geophysical surveying, geotechnical investigations, and then using that information and data to really characterize the site conditions and develop ground models for projects such as wind farms. Fugro has over 50 years experience working in the marine infrastructure industry, and obviously the last 20 years have been heavily focused on offshore wind projects in Europe, the US, and now in Asia. So we have been quite active in supporting those development projects. I work in the Norfolk, Virginia office, which is on the US East Coast, and we are the lead office for renewable projects for Fugro in the US side of things. And I thought this was a interesting slide to start out with. As you know, there's only 7 turbines installed in US waters right now, and the first 5 were installed and constructed off of Block Island. And most people, when they look at present a picture of a wind farm, they present the pictures of the blades and the cells and the superstructures, and those are obviously very interesting to look at. But I thought this was an interesting perspective of what the seafloor looks like after construction of the Block Island wind farm. And Block Island has 5 wind turbines, and in this view, there's turbine 3, 4, and 5, the western 3 that are labeled there. And you'll see a little rectangle that's the base of the foundation on the seafloor. And then I've got highlighted in there the cable trench, and you can still see the cable trench in this from the survey data. And then on particular, like wind turbine generator number 4, you can see four large pads just south of the square, and those are the imprints from the installation vessel that was used to construct or install the turbine themselves. And this work was conducted as part of a BOEM study. BOEM, if I'm not sure if folks have heard of the RODEO study, which stands for, I just have to write this down because it's a mouthful, Real-Time Opportunity for Development of Environmental Observation. So BOEM had an interest for the early wind farms in the US waters to observe, make observations, environmental observations during installation operation wind farms, really to try to understand, what happens during installation. How far does noise propagate in the air? How far does it propagate in the water column when driving piles? What are the impacts on the environment? So Fugro is part of a team, including several consortiums, URI, HDR, and a number of other folks, where we had conducted several studies during the Block Island wind farm, and then also the Virginia coastal offshore wind turbines that were installed this summer. things that I were involved with, I managed the seafloor disturbance and recovery monitoring, where we looked at disturbance of the seafloor and how fast did it take the seafloor to recover after construction activities had occurred. So we conducted repeat bathymetry surveys, and within about 2 years, about 65% of all the scarring and features, disturbance of the seafloor were pretty much not observable in the seafloor, and, restored to its original bed form characteristics. And so that was a pretty interesting study that we had done for that. We also tested some scour monitoring devices that monitored scour at the turbine foundations continuously for over a year. We also conducted observations when they installed the cable with a jet plow. We monitored for evidence of a sediment plume in the water column and how far away from the trench that the sediments deposited and deposited onto the seafloor. And I think what was very interesting is that the actual observed footprint of that sediment was significantly less than what was modeled. But that's what this study was really designed to do, is really, we have intelligent people who can do modeling, but then what really happens in the environment? Are we overly conservative, underly conservative? And so that's what this study did, is try to help BOEM understand these things so they can better regulate and provide guidance on construction observation of the wind farms. We also conducted a benthic recovery around the turbines and monitored how the benthic environment changed around the turbines over the course of 2 years. Some other studies that were interesting were noise measurements during pile driving. Did bubble curtains have an impact on mitigating some of the noise factors at offshore Virginia? We're doing some biofouling studies on that. And if you want to know more about the different studies that have been conducted as part of that program, you can look up BOEM OCS study 2018-029 to find the first phase of the program, or I can email you a list of the studies or other reference material if you're interested in knowing more about these things. But I think really commend BOEM for taking this opportunity to really try to ground truth what happens in the environment out there during construction and operation of the wind farms. So Deanne did a great job of describing an overview and timeline of these G&G surveys and how they're conducted and how they serve to support the development of the wind development and the foundations and the cable planning. But this is going to be a little bit deeper dive in some of the sensors and types of data that are there and how we're using the information. But really, in a nutshell, if you look at the little block diagrams in the center, from top to bottom, left to right, the starting point really is we don't know much about the seafloor and the subsea floor conditions and how they may impact construction operation of the wind farm. So we typically start out with this geophysical surveys, and we start to get a better picture of what's going on the seafloor and get a better idea of what's in the subsurface below the seafloor. And then after that, we conduct geotechnical investigations using the CPTs and boreholes that collect samples. And then we take those samples and test them in a laboratory to better define the strength properties and other engineering property characteristics of the soil and the rock. And that's used to develop what we call an engineering ground model that really it defines the layers, the strength properties of these things, and then that feeds into the engineering analysis and design, so we can try to get the design right for the foundations and the cables. And then try to optimize that to balance, cost of installation, cost of construction, and make sure that the structures are engineered safely and can withstand all the processes that occur in the ocean. But the data are not just used for engineering design, they're also used to support the archaeology studies and the environmental studies, and Drew is going to show some examples of that for one of the sites in the New England area in his talk. So the geophysical surveys, typical large vessel offshore survey utilizes a variety of sensors. Some of the sensors are hole mounted, as Deanne pointed out, some are towed. Some of the hole mounted sensors are multi-beam. They're used to measure the seafloor elevation. Also, the sub-bottom profiler is commonly mounted on the vessel, and that images the shallow subsurface. Some of the towed sensors are the seismic reflection systems. They are towed shallow, closer to the water surface, and they have a streamer and a sparker that provides us the seismic energy source, and that is used to illuminate the subsea bed, and then we develop pictures of the subsea bed. Some of the towed sensors that are towed closer to the bottom are the side scan sonar, and that's used to take pictures of develop pictures of the seabed and look for shipwrecks and rocks and sandways and develop detailed pictures of the seafloor. And then there's a magnetometer that's towed the lowest and closest to the seabed. The magnetometers are typically towed, try to maintain within 6 meters, anywhere from 4 to 6 meters of the seabed, and then to help monitor for the species in the area. There may be a passive acoustic monitoring system, typically at night or low visibility, that's used out there to be able to detect for species in the area and determine their distance. So the geophysical data, we generally break it out into seafloor mapping systems and then subsea floor mapping systems. The seafloor mapping systems, the multi-beam, the side scan, the magnetometer, really used to characterize what's going on in the seabed. So the top two images, you can see very high definition, high resolution multi-beam systems. For wind farm work, we want very accurate depictions of the seafloor and for elevation changes and identify features. And they may be rock outcrops or boulders, or on the right, those are a series of sand waves. And so we want to be able to develop very accurate elevation models of these features that support the planning and design. The image in the lower left, that's a side scan sonar image. And it's really interesting that the resolution of these systems we're using for the wind industry. The wind industry is really driven innovation and technological developments. I think Deanne, I heard her mention that she's really interested in technology and developing that. And I think for us to work in the wind industry, it's an exciting time because the industry has needs that for technology that didn't necessarily exist before. So the image in the lower left, you can see these rocks, these boulders. They're anywhere from 30 centimeters to more than a couple meters in diameter. But in some areas, there may be a lot of them. So in order to map these things, we've developed techniques that use artificial intelligence and machine learning to automatically map all of these boulders on the seafloor, rocks on the seafloor. And then those sand waves that you can see in there, those sand ripples, really, those are somewhere between 2 and 6 centimeters tall. So I always like to think of, look at something around for a size of that. I measured my hand, yesterday, and it's like 10 or 12 centimeters long. So it's really like the half the size of your hand, or your child's hand is like the size of those ripples that you're seeing in that. So it's really remarkable that the technology that's been developed to support this industry is really exciting. And then on the right is a magnetometer data set. We collect that and process that. So you see these little color anomalies. They represent metal objects. They could be any kind of metallic debris or pipelines and cables or UXO or things like that that we use to survey for and identify. So the subsurface, I think you saw some of this in Deanne's, but yeah, we generally use two systems. One's a shallow system, a sub-bottom profiler, people refer to it as, and it can have vertical resolution on the order of 10 centimeters. And it really is used to image the upper 5 to 10 meters and support cable installation, archaeological studies to identify paleo landforms in the subsurface. And support the cables. The cables are typically installed in the upper 2 to 3 meters. So this type of technology works well for the cable, supporting the cable planning. Then we look at a little bit deeper to support planning design of the foundations of the turbines and the offshore power substation. Depending on the turbine foundation type that it uses, would drive and dictate how deep we want to look. Monopiles, those are the single piles. Those can be on the order of 30 to 40 meters deep installed 30 to 40 meters deep below the seabed. Jacket foundations would have 4 small piles, and those could be on the order of 80 meters deep, driven 80 meters deep below the seabed. Offshore power substations also have typically deeper penetrating piles on the order of 80 meters. But then there's like suction bucket or suction caisson foundation systems. Those are don't penetrate very deep. They're only a meter or 2 below the seabed they would penetrate. Or a gravity-based system, it might look like a chess pawn piece set on the seabed, and so those don't penetrate as deep as the pile foundations, but they have other things that make them attractive or less attractive as a solution for a wind farm. They're sensitive to water depths and bottom seafloor bottom soil properties. So each project has opportunity to utilize what they feel works best for them. I would say most wind farms are using monopiles these days, and probably the second most popular is a jacket structure, and then suction buckets and gravity bases are probably make up the next level of foundation types. So how do we collect the geotechnical data? The geotechnical boreholes are usually collected using a drill ship. This is one of ours that's based in the U.S. and the Americas that works on the wind farm projects. And there's a big drill derrick in the middle, and it holds position using a DP system, no anchors. And it's able to do soil boreholes or cone penetration tests. And the boreholes are typically between 40 and 80 meters below the seabed. The shallower geotechnical tools support mostly the cabling work, or there might be a need to do something shallow, like vibrocoring for some of the shallow wind turbine foundation concepts. And these are, vibrocores and cone penetration tests. And they usually test to a depth of about 3 to 10 meters below the seabed. And the coiled CPT, it gets lowered to the seab floor and then pushes a probe into the ground. And then the vibrocore gets lowered down and actually vibrates, the head vibrates and advances the core barrel, and then is retrieved and pulls a sediment core back up that's 3 to 6 meters long. So how does that data all kind of come together? How do we use it? These are some examples how we integrate the geophysical and geotechnical data. The image on the top right, that's an example of a seismic record, and the yellow vertical stick with the red squiggly lines represent the geotechnical data. And the red line represents relative strength of the soil, and then we have soil layers that we interpret from those data and determine the strengths of those layers. And the middle image is kind of a cutaway. You can see the interpreted three-dimensional surface of the soil layer as we kind of pull away the seismic data. And then, and the lower image, illustrates it, that it's all used to develop a 3D site model or a ground model for the site, that we can determine what the soil layers are and the strength properties are, on the site. The image on the left is just an example of where we've created one of these 3D surfaces of a geologic unit here in this case, and you can see the seismic data that's shown there to illustrate how it's been integrated together. And then we've placed a cable in here in this case, nominally 2 meters below the seabed, where it might be installed, and then we can use that to understand where this cable in the trench may intercept this geologic unit, this layer that we were evaluating. Whoops, wrong direction. So I think now what I'd like to just step through is how does an example of how this information, these phased investigations, can be used to inform the planning of a wind farm. And there's two general concepts. One is the phased approach, and Deanne did a really nice job of describing what that sequence looks like, how the different phases of investigation, how the different stages of the ground model are used to advance the planning and understanding of the project. And there have been projects that are, maybe the sites are small enough that they can do a full site survey and full ground investigation in 1 year, but typically that's very unusual. And they would go to a phased approach. And this is a completely hypothetical site, but schematically, I think it kind of captures what we've been talking about. So you may have the developer may have a lease, obtain a lease boundary, and maybe they don't have a need to develop the full lease, and they want to develop it in phases. So one strategy might be that they do a regional or reconnaissance geophysical survey of really widely spaced lines. They could be 900 meters apart or even wider apart than that, and that's what the blue lines represent, are kind of a regional survey. And they may go out and collect a couple of geotechnical explorations in the area, a couple of boreholes and some CPTs to try to get an understanding of what the subseabed conditions are like across the site. And that's used to develop an initial, ground model. And there might be some areas out there that represent constraints for construction. They could be environmental, they could be engineering constraints, it could be geohazards, archaeological resources, and it could be anything. So they could be scattered throughout. There might be areas that they're more prevalent of these conditions. But maybe in this case, they decide to break this up into 2 phases, and the leases could be broken up into more than 2 phases even. So phase 1 is the one that the site or the phase that might move forward in this story. So they may say, well, we have an interest in developing 800 megawatts of power. So we would need, if we're going to use a 10 or 12 megawatt turbine, we may need to plan for 100 of these turbines, and we'll put conceptual locations out here for 100 of them, but we're going to survey collect some more data on the site and do additional geotechnical investigations. And then once we do that, we have a better idea of the understanding of the site conditions and some of based on the new survey data, maybe some of the locations were not favorable or were removed from the planning session. And then we have to take into consideration that there's cables that have to be connected to these turbines. So as we do more surveys and gain more information about the sites, then we develop a better understanding what the inner array cable layout will look like, and what the export cable route will look like, and where the power substation will be. And so then, there may be a need to do some specialized surveys if the project deems that they're necessary, a 3D seismic or UXO survey, or a more focused survey on a specific area of the site if they feel it's necessary to conduct that. But at the end of the day, one of the things that that's required to satisfy the lease's stipulations is that BOEM requires some studies that are part of the COP submission process, and it really, what they're doing is that they're looking at areas of potential effect. Those would be areas that could be disturbed, where the seafloor or the subseafloor could be disturbed due to construction, installation, or operation or maintenance services of the wind farm. So within that APE, they call it, then they have certain survey requirements that they have to fulfill in order to clear or prepare and prepare the reports, the archaeology reports, the benthic reports. And so that survey requirement, again, there's two strategies for that. You could either survey the entire lease area or the entire phase, but the blind spacing is pretty tight and strict. It's a 30-meter line spacing in the primary direction, 500-meter spaced tie line. So doing 30-meter line spacings over the entire lease area is a pretty significant effort. So so there's other approaches that the projects can take where they'll do a corridor survey approach. Well, they'll maybe survey a corridor centered on the turbines that will be wide enough for the installation vessels to get in and do the work, and then also a corridor where the cables will go. And those could be on the order of 200 to 400 meters wide on the turbines, or in the cables, 180 meters is the minimum survey corridor width that BOEM requires, but they can be, up to 200 or 400 meters wide, or wider if the developer wants to make the corridor a little bit wider. So that's kind of what the little green shaded area represents, is what that corridor would look like. So the developers are not required to survey every inch of the lease or every inch of the phase, just where the seafloor is going to be disturbed during construction or maintenance of the wind farm. So with that, I just want to say thanks for your time and opportunity to speak with everybody.
Thank you, Kevin. That was super helpful. Any questions for Kevin before we go to Drew's presentation, and then we'll try to reserve time for a full Q&A at the end. Don't see any hands, so Drew, on over to you.
All right, let me go ahead and share my screen.
Okay, well, while you do that, we did just get a question, in fact, for Kevin, which is, are any of the survey vessels in the region US built?
Yes. Some are, but not all.
Yeah, thank you. Obviously, the Jones Act is something that has controlled us for generations. So that's interesting that you've got at least some of them built US. Hopefully there'll be plans to do more of that. Some of us were around when a lot of foreign vessels were eliminated from the US EEZ. So it's kind of difficult to accept that we don't have everything being built here in the United States to do this exploration. But I just wanted to make that comment. But it's really a great presentation, and I appreciate you taking the time to do that. And I'm surprised that any are built US, frankly. So that's good to hear.
Yep. I can tell you that it's not just the US that's busy with offshore wind, Europe and Asia as well. So there's a really strain on resources globally to support the engineering, surveys and studies, and it's all the regions are competing with each other. But yes, we wish, Fugro wishes we had more vessels, and they could be US based and to support it. It's just this industry really came up fast. We were hopeful, we knew it was coming, but getting the vessels built and again, they're you have to remember that the industries for some of this geophysical surveying, some of these are specialized vessels, and they're in the Gulf of Mexico is where the industry for oil and gas has existed, and those vessels are not always the right ones for this work, but yeah, it's just the volume of work just came up really fast.
Well, thank you for that, Kevin.
If I could just quickly add to that from the developer's perspective, we absolutely prefer US built, but as Kevin pointed out, there aren't enough to support all the activities that are ongoing at the moment. Atlantic Shores currently our primary geophysical vessel is a US flag vessel, and it's a Fugro vessel. We're very, very happy with that. So we definitely look for that opportunity and factor that in when we're selecting our vessels for our work. So I appreciate that comment.
Great, thanks. So moving on, slightly different topic to sort of environmental impacts with our old friend Drew. Go ahead.
All right, thanks, Annie. I'm going to shift really from the engineering perspective, a little bit of overlap with what Deanne and Kevin spoke about, into really the permitting side and also really the areas that I think have a significant interest to the fishing industry. So in other words, the environmental conditions. So I work with Inspire Environmental. We're based in Rhode Island, which is the we think of as the jumping off point for the offshore wind industry in the US. And we have been involved for about 10 years from the very beginning of the Block Island Wind project, and learned quite a bit about the kinds of data that would need to be collected as everyone was learning from that project. So Nancy asked if I could address 3 questions. What do these geophysical surveys tell us about the kinds of habitats that are used by fish and invertebrates? What are potential effects of the activity of the geophysical and geotechnical surveys? And what, if any, monitoring could tell us a bit more about them? So I'm going to start with really the engineering side, which is that during a geophysical survey, as Kevin mentioned, there's a need to collect direct evidence of what is on the seafloor. So most of the techniques that he described are remote, utilizing largely acoustics to gather the data. So within the BOEM guidelines, there's at least 3 methods to gain information on the very shallowest part of the geophysical data. So in other words, just the surface sediments themselves, not that deeper conditions that would require vibrocores or boring. One of them is a grab. You can see one on the upper right there. Pretty traditional technique. It's been around for well over 200 years. Technically, this is used to collect a physical sample, which is then sent to a lab. It's dried and it's passed through a series of nested sieves. And you then weigh the amount that remains on each of those different size fractions. So you get a quantitative analysis breaking the sediment into its component pieces. An additional approach is to attach some kind of imaging to that grab. It's generally a video camera. Has really 2 purposes. One is to determine if the grab is about to contact sensitive resources and try to avoid them just by simply not lowering it. But it also gives us information about the surface features. And Kevin gave the example of these small ripples that were the size of a child's hand. We're in the scale there where you'd be able to define and examine those kinds of features. The third approach, which I'm going to expand on a little bit here, is an entirely a visual approach. This utilizes a couple of different camera systems to get grain size from visual data. It has the additional ability to look at layering under that shallow surface, as well as collecting surface features similar to the grab video. So both grabs and visual data can be used for answering the question of what is the habitat? And habitat is really the combination of the physical features, the characteristics that define it from a geological perspective, and then the biology that is supported by that physical condition. BOEM requires that we report out these habitats in a classification system that I'll just call CMEX. I'll refer to it a couple of times. So it's the national standard, and it is required for all of our reports, for all of this data to be pulled together into that classification system. So now I want to take you on a little bit of a tour of the tools that can be used, and then how that data sort of plays out as you integrate the data that Kevin collects with the data that we would collect, sometimes on the same vessel. This is the system that we use. It is a combination of 2 different cameras, a sediment profile imaging camera and what we call a plan view camera. So I'm going to show you a cartoon of how it works. The whole system is lowered to the seafloor on a wire. When a weight contacts the seafloor, it releases a trigger. And there's a synchronous strobe and a downward looking camera that takes a downward looking image. We call this plan view, as if you had a plan of a house. So this is an example of an image from a site. The scale here is about 1 meter across. The 2 little red dots there are 27 centimeters apart. So we use those scaling lasers to know exactly what we're looking at. So obviously here you can see some biology, you can see a rock, you can see some sediment features. Then this entire system is lowered right down onto the seabed, and weights push a prism down into the seafloor. So that sort of cartoon you can see on the right there, that's what we would call an upside down periscope. So the profile is pushed in and we get an image that looks like this. So the prism has a relatively undisturbed slice of the top 20 or so centimeters of sediment. This is the biologically active zone. And we capture a picture, we pick up the whole system, and we drop it again. So we take multiple stations or samples at a given station. We don't actually collect any physical stations or material. What's really important about this image that I'm showing here is, one, we have a undisturbed surface, so we get a very clear idea of what the conditions are. But we're also revealing that in this case, there are two very different types of sediment at this particular location. One of the challenges of using a grab and sieves is that all this would be mixed together and you would get a distribution of different sediment types, but it would be less clear that these were actually two different events in this particular location. So this approach gives us a combination and integration of what we would call ground truth. So as Kevin is interpreting his side scan or his geophysical data, it's useful to know what is exactly the condition at that spot. And at the same time, we add the biological data, both the activities of the animals, what they're doing to the sediments is as important as which particular animal is there. I'm going to walk you through sort of a zoom in to one of the samples or the sites that Kevin mentioned. This is an example. It's a case study of the South Fork project. In this case, the lease area, this is the smallest project proposed in the Northeast. And the site is small enough that a full 100% geophysical survey was done. It makes it a little easier for me to illustrate things. You can see its proximity to Block Island. And you can also see the quality of the data that existed prior to the collection of this data. It's useful, but it's also quite coarse. So we don't see a lot of detail outside of this. The footprint you see here is the extent of the geophysical data that was used for site characterization, which then moves into all those documents that both Deanne and Kevin described. I'm going to zoom in and describe 3 layers of data here. They're one of many sources of data, but they sort of illustrate the point here. The first one is called backscatter. This represents the acoustic energy that comes back after the multi-beam signal contacts the seafloor and bounces back to the receiver. Those areas that are in the warm colors, the hot colors, have either a denser surface or a more complex surface, and they bounce more sound energy back to the vessel. The cooler colors are areas that are smoother or softer, and more of that acoustic energy is actually absorbed into the sediments and doesn't get back to the receiver. So this is a quantitative assessment that is, we find, extremely useful for delineating habitats. What you're seeing in addition to this is what we call hill shading. So this is where Kevin's team would take the bathymetric data and model it so that you are sort of creating what looks like a 3D surface. The dots, the colored dots, are where our samples have been taken. So small area, relatively high density of stations were collected here. And again, an effort was made to try to characterize the distinct areas of the seafloor. So I want to move into that. So here's an example of what the camera system collects. These images on the left are paired. So there's 3 downward looking images and 3 profile images. I've zoomed in on one of them to show you that in that particular circle, in an area with hard return from the backscatter, indeed we find some gravel on the surface, and in general, a mix of sand and sandy gravel at this particular location. So that's the CEMEX that I was describing. This is one of only many different kinds of classifications within CEMEX. You can see on the left There's a bunch of them listed there, including the biology. As we move to an area that has a softer return in the backscatter and a different signature in the hill shading, here we see a well-sorted sand. Each example has very similar kinds of sand. We can also see those small ripples that Kevin had described previously. So this provides some very clear indication of how to interpret that area of the map. This represents the interpretation that Kevin's group did based on the geological characteristics of the sediment. So there is areas which have a lot of boulders, what we call glacial moraine, areas with coarse sediment and relative concentrations of boulders, and then the sand and the muddy sand areas. You'll notice here that this is now interpreted data. It's not the raw backscatter data. And here we've picked out an area which we've classified as mud and sandy mud. And you can see from the imagery that not only is the camera sunk quite a bit further, so we know it's a softer material, but we can see that it's very difficult to make out individual grains, just enough to know that this is actually muddy sand. It looks like mud, but there's a fair bit of sand in these images. And this is a very good example of how we see the biological activity inside of these sediments that have a huge impact on the quality of the habitat that both invertebrates and fish would make use of. So now we've reached that sort of crossover point between the engineering information and the habitat that would provide information about what different kinds of habitats are present. These are then reported in requirements for essential fish habitat. Are they providing spawning habitat, juvenile fish habitat, refuge, food resources? We have to interpret these habitats based on the biology that's there and the conditions that we see. So this is a good example of how we begin to learn something beyond the engineering information, one which I think is probably of great interest to fishing community. My son fishes out in this area, and certainly he's very interested in getting a better idea of what the bottom looks like. I want to move on to the second question, which is lay a little bit of groundwork for how these instruments may or may not affect fish and invertebrates during the surveys. So first of all, it's important to know that fish and invertebrates have relatively specific sound frequencies that they utilize. So it's not that different really from humans. We have a certain range of sound frequencies we use to communicate within our own species. A dog whistle, for instance, is unavailable to us. We can't hear that, but it is obviously something that a dog would make use of that sound. So within the species, most of the communication is largely related to reproductive activities. And again, I'm not talking about marine mammals here. I'm focusing specifically on fish and invertebrates. Then outside of their own species, a lot of the sound is utilized to try to either avoid predators or find prey. So most fish and sharks and rays have adapted to utilize sound frequencies that are relevant to these goals that they have to either reproduce or find prey or avoid being eaten. Layered on top of that is all the noise in the environment. So as we operate in the ocean, whether it's drilling or fishing or vessels or whatever our activity may be, we're putting sounds of a variety of different frequencies and natures into that same environment. So this can create obviously some interaction and confusion for those other species. So sound in any medium travels as a wave. So you get a pressure wave. We can experience those pressure waves physically, but by and large, the way animals detect sound is through particle motion. So there's some within our ear, we have little moving elements within our ear. Fish and invertebrates also use those to detect that sound. I want to also make you aware of a really great resource. This is a website that's been around for quite a long time, but it's very frequently updated. This is called DOSITS, for Discovery of Sound in the Sea. It has a lot of great introductory and more advanced information about sound, far more than I understand. And again, it's a great resource. So one of the things that website points out, and I have learned from talking to my colleagues in this field, is that if you're not utilizing some sort of a sensor, the sound pressure generally moves right through a body without really having any effect. So in other words, that pressure wave moves through the body. If you have a sensor designed to detect that frequency, you're gonna be aware of that sound pressure. So very briefly here, with sound in fish, many fish have an inner ear. So there's a small particle called an otolith that is moved around by that sound pressure and basically impinges on hair cells. And so it's really the particle moving that the fish are paying attention to, not unlike our own eardrum. For these fish, they're really down in very low frequency sound. So I'll be talking a lot about frequency here. We generally think of measuring them in hertz, but many of the sound sources that we're going to talk about later are measured in kilohertz. So I have to kind of go back and forth between those. Then the lateral line is something most people are familiar with. Generally, that is detecting sound pressure waves very close to the fish. So there's little teeny hair cell receptors there that are, again, at very low frequency relative to a lot of these other sound sources. And then we were aware of swim bladders. Not all fish have them, but they are going to respond to sound pressure. And in general, they're creating a particle motion within the swim bladder itself. And the inner ear can then detect that. So fish have been grouped into these three groups. I'm not going to go into a lot of detail here, but the three groups at the top are really using very low frequency, basically 1 to 3, or just basically below 3 kilohertz. And the next group are a small group of fish that have a swim bladder that's connected closely to the ear. Herring is a good example around here. And they can actually go above 3 hertz or 3 kilohertz, and in some cases as much as 100 kilohertz. So it's worth remembering there's these two groups of fish. There've been a lot of experimental work on fish, and there's something that's defined in the industry as an acute criteria. This means it's an injury at that level that a fish may be affected for a period of time. It could be hours or days, but it's not going to create mortality. There are other criteria that are higher than that. There's two ways of measuring it. One of them is to average the sound. So for non-impulsive sounds, you generally look at an average of the sound over a short period of time. For impulsive sound, you would look at the peak because the impulse is a very short time period. You don't want to degrade that by averaging it. Marine invertebrates a little different. First of all, we don't have a lot of understanding of their ability to detect sound. We're really focusing on true groups here, largely because of their interest to commercial fishing. For the crustaceans, those that have these exoskeletons, as you well know, their bodies are covered with hair and little sensory organs. And again, they're detecting particle motion at a relatively low frequency. And then some of them have these organs inside their appendages that again detect particle motion, and you get a variety of different abilities there. Then some have statocysts, and this is very similar to an otolith in a fish. So it's a small, essentially hard little thing that moves against hair cells. And so we know that longfin squid and octopus, two important species in this area, can then detect particle motion at a little bit higher frequency than these other sensory hairs. So again, we know something about the range. There are no acute criteria established for invertebrates and relatively limited experimental studies. So to try to summarize this, I've pulled together a table where we're looking at really 3 different categories of sound sources. I'm going to start with the top one, move across, and then down. So the first 3 are tools that Kevin described. I'll start with multi-beam. Important thing about multi-beam is it's a series of beams that are spread across the seafloor. So they extend to the port and starboard of the vessel for quite some distance. So we call that a swath. It's very narrow in the fore-aft distribution because you're trying to get a very precise signal down to the seafloor. And that signal moves across the seafloor as fast as the vessel is moving. And according to Kevin, most of the surveys that are being conducted now for offshore wind are utilizing a 400 kilohertz signal. So that is a relatively high frequency signal. The reason for the high frequency is it improves the resolution of the data that we then use to conduct these maps. The next column over is if you measure 1 meter away from that source, so in other words, directly below the vessel, just a meter away from the multi-beam, you would get an average, and I think it's averaged over about a very short period of time, 220 decibels. In water, that's a very different level than you would sort of think of in air. So as we move across, what it means is at the 400 kilohertz frequency, none of the fish groups are tuned to really pay attention or have sensors associated with that frequency. So there are some circumstances where there may be some invertebrates that may be able to detect, but we don't know a lot more about them. The next 2 categories, these sub-bottom profilers, are essentially not a swept out to the side, but they're narrowly focused directly below the vessel, again, moving as fast as the vessel over the bottom, and very, very focused. You may have noticed that when he talked about these profiling images, it's basically a vertical slice down into the sea floor. So that energy is focused on just one spot as it moves along the bottom. These are considerably lower frequency, depending on the purpose, and as you try to get deeper into the seafloor, the frequency will change. And again, the average decibel level is somewhere between 175 and a little over 200 decibels. These frequencies are in that last group. So the larger group of fish are not tuning into these frequencies, but they may be detected by herring, menhaden, things of that nature. And so again, that acute criteria would apply if that herring is 1 meter away from the sound source. As it gets further away, that decibel level is going to degrade relatively rapidly. The next group, the sort of orange pattern down there, are what we know of sort of existing sources that are common in the area. There was one study of ambient noise in Rhode Island Sound, basically putting out sound sensors. Again, these are not impulsive sounds, and they're also at a relatively low frequency. Again, the average was around 130 decibels. And the frequency is such that this sort of clutter noise, if you like, is something that could be detected by most fish. But again, the normal average intensity is not real high. Fish finders are very commonly used. They're very, very similar to multi-beam echo sounders, except they're what we would call a single beam. So they're not swept out to the side. They're looking directly below the vessel. As I'm sure all of you know, you can use them across a range of frequencies. So the frequency that's used is quite important. The energy that is driving that echo sounder in order to get a decent return of what's in the water column is going to range across the decibel ranges you can see from 150 to a little over 200 decibels. So these frequencies then do overlap with the herring and the menhaden. And again, they would have to be quite close to the fish finder to be experiencing that kind of sound energy as opposed to frequency. The last 2 are quite different. These sub-bottom profilers that are towed behind the vessel, they radiate sound, an impulse out in all directions. and then the receiver receives the data that's coming back up to that sensor. These are then at a very low frequency in order to penetrate deeper into the seafloor. And in general, these, because they're impulsive sources, they're measured at peak. So again, you can see these peak values. Should a fish in the first group be right underneath that towed source within a meter of it, that would be exceeding those acute criteria. But as the fish get further away from the actual source, then that decibel level will drop off relatively quickly. So this is a summary of what we know at the moment about fish. I haven't added invertebrates because there's so little we know there. But I hope it provides a little bit of context about potential effects of geophysical surveys. Obviously, the equipment that touches the seafloor has a physical disturbance. That's a little different. The last thing I just want to touch on is there's been a lot of questions about how could we potentially assess the effects of these surveys in the region. There's obviously been a lot of activity over the last few years. One of the things that we're proposing, and this is specifically for one of the lease areas, is to, as the baseline data is conducted, this first set of data that we've described is to characterize the site. We will now begin collecting baseline data on fish, lobsters, Jonah crabs, and the benthic habitats. And that will proceed for several years before the project is actually constructed. So after talking with fishermen and talking with other scientists, we're suggesting that we would call a control area, and an area that would not be directly affected by construction, that these control areas be deliberately located outside of the footprint of the direct geophysical survey activity. So for that reason, we need to know where all the geophysical surveys have been conducted, find areas that are comparable habitat to the area where eventually construction, if it's permitted, would occur. So for at least 1 or 2 years, we can collect some data and compare areas that have had geophysical activity with areas that have not had it. So that's one way we may get a little additional data. In this case, this is a lobster survey. We can get some data on invertebrate abundance and their condition during those times, and compare it with areas that have not had any geophysical data. So that's all I have. I'll pop off my screen for the moment and happy to answer any questions.
Great, thanks, Drew. And I do apologize to everyone on the call for misjudging the amount of time that we should have reserved for this. But if anyone is able to stay on and does have questions, you can raise your hand in the chat box or raise your hand in the participant list, write in the group chat, or you know, for those that are on the phone or can't use that, feel free to jump in. And if if you need to wait, I'll let you know. How's that?
I guess I have a question. I'm not sure I can type fast enough before you move on. But
Go for it.
thanks, Annie. Yeah, it'd be interesting. That sonic information in that last slide was really interesting to see the overlap from the different sources. Really surprised me, frankly. I wonder where a vessel engine would end up, you know, in comparison, say, to a bottom sounder. And we do use multi-beam sonar in the fisheries in the region, particularly for the 2 species you just mentioned,
Right.
and you know, the sensitive bladder type fish. So without taking up a lot of time, I just kind of wonder where the engines would end up on that chart.
Well, they're in that ambient noise range. So obviously they're not impulsive. I do have another chart, which I'll try to pull together and add, which does have some information on it depends an awful lot on the type of vessel. You can imagine if just with your own hearing that the frequency is at a low sound, is at a high sound, it varies quite a lot. But it is obviously a source of noise. It's obviously right at the surface. As I'm sure you know, low frequency noise travels further than high frequency, but it is an additional source of of sound energy in the ocean. Absolutely.
Thank you. It's very interesting.
Great. Okay, I see a question in the chat box. See a couple questions in the chat box. Okay, the first one's from Scott Mackey. So Scott, feel free to jump in. I'll read it out. As we identify key habitat within the lease area, how do developers relocate their array, and is this required?
I've been working on that quite a bit. What we are doing is developing very, very detailed maps of these habitats. So when you say key habitat, it's all in the sort of the eye of the beholder. One kind of habitat can be really crucial for Atlantic cod spawning, and another habitat may be important as a food source for a different fish. So those have to be weighed up, and they are really reported to the NOAA Habitat Division, and then they come back with recommendations about effects on those habitats. However, what I can tell you is the habitats in the Northeast that have the highest value in that respect happen to be the same habitats that present really challenging engineering problems. So boulders, cobble, gravel, harder bottom. It's more difficult to operate in those bottoms. So the position, particularly of the cables, as you know, the positions of the turbines have been defined by a grid at the moment. So there's not a whole lot of movement there. There's some opportunity, to sort of microsite those a little bit. So absolutely, the effort is made to minimize, first of all, any contact with habitat of higher value. I think it's arguable that any part of the seafloor has some value to some species. So you sort of have to choose your poison in that regard. So I don't know if that helps.
Drew, this is Scott Mackey. The only quick comment I'd make to your statement is that there's a you've exempted out basically all your clams and scallops by that definition. If we're only looking at rocky bottom as the most valuable commercial bottom, I think you're missing some very valuable species to New Jersey's fishermen.
Well, yeah, and I absolutely, again, any commercial species are considered of importance. And so we do absolutely look at the value of the habitat to both the in-place species, those like clams that stay in one place, the scallops move around a little bit. And so again, you're looking about a couple of different things. How extensive is that habitat, and how extensive is the disturbance? So we create a quantitative estimate of the actual disturbance that would occur to that habitat. So for instance, if a cable is being put in place through an area that has heavy scallop fishing, we're going to estimate exactly how much of that habitat will be affected by the installation of the cable. From what I understand about cable installation, and I've studied the Block Island cables and aware of the ones in other parts of the world, the disturbance of that habitat is temporary in that the sediments move back, as Kevin showed, they eventually sort of smooth out. And so there is some level of disturbance to the organisms that are there, but the habitat itself is not permanently altered. On the other hand, if you put a structure on the bottom and you completely cover the bottom in some form, whether it's a platform or whatever it might be, then you're going to alter that habitat for a much longer time. So those are all have to be taken into account. So I hope that's helpful.
Sorry, I'm muted. I was trying to talk. Hey, thanks, Drew. So the next question in the chat, which I think is a little, I think you just touched on this, but from Peter Flournoy, how well is the data about which habitat bottom a species uses coordinated with bottoms that are classified as sand or mud or under various classifications?
Okay, so you're playing to my prejudices here, which is that I study those habitats precisely, the sand, the mud, all those different kinds. And so we both collect data during the surveys as to what species are there, but you also have to account for this type of bottom could support a scallop, a clam, whatever it might be. So absolutely, the whole purpose of the study is to determine what sorts of organisms that habitat would support. So I hope that answers that.
Yeah, thank you.
Great. Okay, next question for Drew again. You're in the hot seat. Why did the Block Island cables fail? I think that's referring to the exposure, and how does that not happen in the future?
So I'll tell you what I know about that, which is that there are two cables. One comes from the Block Island Wind Farm into Crescent Beach, and one comes from Crescent Beach to the mainland. And two different installations, two different responsible parties. My understanding is both of the last segment of those cables had some exposure due to storm energy, and they are planning to replace those two segments of the cable. So every project that I'm aware of now, in terms of how they're submitting their permits, is expecting to do what is called horizontal directional drilling. So anywhere from 1,500 to 2,000 feet offshore, you would dig a pit and you would drill actually from the land side out to reach that pit, thereby putting the cable as much as 20 or 30 feet below the beach. I'm not going to speculate as to why those cables did not use HDD, but they were not placed in that way. So they were relatively shallow. The answer, the way to make them not fail, is to basically drill down, put them well below the surf zone, and then bring them up offshore.
Thanks, Guy, to that for the question. Okay. Any more? I don't see any more hands raised or anything in the chat box. Anyone else got anything for the good of the order? No? Okay. Well, I think I imagine that any of our presenters, I won't volunteer them, but I would probably be happy to follow up questions by email. You know, if you think of things or things come up, these are pretty friendly people that we're happy to work with. So feel free to get those over to us or to Nancy. And we can pass those along if anything comes up. But in the meantime, definitely appreciate everyone's time. Appreciate Nancy for working hard to put this together. And of course, last but not least, all the presenters for their time and work on this. So Nancy, any closing words?
No, just thank you for the presenters for putting together such detailed presentations. We really appreciate it.
Great. Thanks, everyone.
Okay, thanks everybody.
Everybody.
Thank you.
Sure.
Have a good night.
Thanks.
Dave.
Bye, everybody.